Hello, and welcome back to the course Physics 141, Classical Electromagnetism 1. Before we proceed with today's lesson, let's review some of the concepts that we need for this lesson. So we have discussed about Coulomb's law, the general form of Coulomb's law for a point charge, and the integral form of Coulomb's law for a continuous charge distribution. We also have reviewed some of the concepts, some of the types of coordinate systems. We have the Cartesian coordinate system, cylindrical and spherical. The differential length for the Cartesian, area and volume are given as this. The differential length, area and volume for cylindrical coordinates are given also as this equations. And for spherical coordinates, the differential elements are given as this. So we will need these differential elements for our topic this session. So we will now be talking about Gauss's law. As mentioned before, this is advantageous for continuous charge distribution over the Coulomb's law. So if your problem has a symmetry, then it's easier to use Gauss's law. So in this discussion, we will be discussing about the divergence and the curl of the electrostatic field, wherein one consequence of this is Gauss's law. So if we have an electrostatic field, or rather, which may be due to a charge distribution, rho, as a function of r prime, the source points within a volume dv prime, and we are asked to find the electric field, say a point P, a distance r from our charge distribution, then the electrostatic field, since this is a continuous charge distribution, the electrostatic field is given as this. So take note that our charge density rho is only a function of the source points r prime, and we are integrating here over the source point elements dv prime. The separation distance curly r here is just r minus r prime, the separation distance vector. Okay, so if we take the divergence of this electric field, so take the divergence of E, so the divergence of this integral here. So since the divergence operator, the del operator, is just a differential operator, and you can always interchange differentiation and integration. So instead of getting the divergence of the integral, then we can take first the divergence of the integrand and then integrate. But take note that the del operator here, the divergence, only acts on r, the field point position vector, or the field point. So it only acts on r, and in our integrand here, the only term containing r is the separation distance, r minus r prime, and our r hat separation distance unit vector. So the divergence will only act on those vector, or those functions. So rho here and dv prime here are not affected by the divergence operation. Now, you have discussed this. I don't know if you recalled, but you have discussed this in your mathematical physics, that the divergence of 1 over r squared r hat, the divergence of a 1 over inverse square function, is just equal to 4 pi times the Dirac delta function, r minus r prime. So actually the divergence is 0 everywhere except at r equal to r prime, at the origin. So that's what I think that's what you have learned in mathematical physics. So the Dirac delta function is infinite everywhere except at, say in this case, r is equal to r prime. So this term here will now become 4 pi times the Dirac delta r minus r prime, and it's actually very comforting to have a Dirac delta function inside your integral, because if you have a Dirac delta function inside your integral, you don't need to integrate. So whatever function is beside your Dirac delta function, the evaluation of that integral is just the function evaluated at r is equal to r prime, at r prime is equal to r. So in this case, f of r. So you will expect that this integral will just be equal to rho at r prime equal to r. So easy peasy integration if you have a Dirac delta function. So this divergence of the electric field is what we call Gauss law, and this is the differential form of Gauss law. You may have encountered the integral form of Gauss law, and we will derive it later. So what does this tell you? That the divergence of the electric field is essentially the epsilon naught is just a constant. So the divergence of the electric field is essentially your charge, volume charge density. So if you see an electric field lines and you notice that it has a divergence, then that can only mean one thing, that there is a source of volume charge distribution due to that divergence. So divergence, I mean divergence literally. When you say divergence, spread, nagbulag. It's the opposite of convergence. Convergence, nagmeet, fall in love, nagbulag. Divergence. So divergence, nagspread or nagbulag ang electric field lines. So if you see a diverging electric field line, that can only mean one thing. There's a volume charge distribution rho causing that divergence. So if you have parallel electric field lines, therefore those lines or that electric field have no divergence, meaning zero on divergence. If the divergence is zero, zero ang volume charge density. So rho is also zero. But this doesn't mean there isn't a source of electric field. It just tells you that there's no volume charge, but there could be a surface charge, like what we have discussed in the previous lesson, where if you have an infinite sheet of charge, its electric field is actually like this. It's parallel lines. It's not diverging. It's constant everywhere. So you have to take note that even though the volume charge density is zero, the surface charge or the line charge density is not necessarily zero if you apply Gauss's law. Now, this is a simplified version of Gauss law. So del dot E, the divergence of the electric field, is just rho over epsilon naught, the charge distribution. Now, what if we integrate this? Integrate both sides over the volume dV. So epsilon is just a constant. We take it out of the integral. So integral of rho dV. So the integral of rho dV, this is just, rho dV is just dq, the differential charge in a volume charge distribution. So basically this is just dq, and an integral of dq is just q, the total charge. So q. So basically this term here is just q over epsilon naught. And if we use divergence theorem, which you should recall based on your mathematical physics, the divergence of a vector, the integral of the divergence of the vector over a volume V is just equal to the dot product of the closed integral of the dot product of that vector dot with the differential area vector. So take note, this is a closed integral, closed surface integral. So you need to integrate over the whole surface. So this is the integral form of Gauss law. I think this is the one that you are more familiar with because you have encountered this in your Physics 41 course. So usually in your Physics 41, you call Q as the charge enclosed by your Gaussian surface A. So A here is the area of your Gaussian surface. And this whole term here, this whole integral, which is just equal to Q over epsilon naught, is what we call the electric flux. So flux is another word for flow, but So you can think of this integral E dot dA as the amount of electric field that flows through a certain area A. But I have to take the word flow in quotation because the electric field is actually not flowing in this case, because this is an electrostatic field. Take note, we are still in the part of electromagnetism called electrostatic. So the field is not changing with time, it's static, it's not moving. So later when we go to electrodynamics, the electric field in that case is now changing with time. So here, if you have an electrostatic field, it's actually not flowing in this case. So what does the integral form Gauss law tells you? So if you have a Gaussian surface, for instance, you have a Gaussian surface, and of course it has an area, and it's perpendicular to the surface, the Gaussian surface. And if you notice that there are electric field lines coming out of that Gaussian surface, and if you take the dot product of the electric field and the area and sum it over all the differential area, and you notice that the value is not 0, then that could only mean one thing. That means that there is a charge enclosed by that surface. So that is what Gauss law, the integral form of Gauss law, is about. So it's about the charge enclosed by your Gaussian surface. Similar to the divergence, the differential form of Gauss law, wherein if you see a divergence, then that means that there is a volume charge distribution, which is a source of that diverging electric field lines. So note that this is a dot product, and the definition of the dot product A dot B is equal to AB cosine theta. So you can, E dot dA is just EDA cosine theta, where theta is the angle between the electric field vector and the differential area vector. Okay, before we proceed with an example, let's review some vector calculus formulas. So I will be presenting to you a summary of the equations in vector calculus, but try not to be overwhelmed because this is a lot of equation. So for instance, let's start with the position, three-dimensional position. So it's just x hat plus y hat or z hat. The differential position will then be the addition of the three differential lengths. We have the three differential lengths, right? The x hat, the y hat, and the z hat. If you add those three, then you get the differential position vector. Okay, what is this one? This is the gradient operator. So gradient of a scalar function. The gradient of a scalar function is now a vector. So it's a vector. It's a three-dimensional vector in general. So the gradient is from the word gradient, literally gradients from dark to light or from intense to less intense. So gradient. So for instance, the gradient of potential energy is force. So if you take the gradient of, say, gravitational potential energy, then you will get gravitational force or weight. So for instance, gravitational potential energy, the potential energy goes actually higher as you go up, and meaning in general the force is the negative gradient of potential energy. So if your potential energy's gradient is in this direction, it's going higher as you go higher, then the negative gradient of that is down. So the direction of the weight or the force due to gravity is downward. Okay. This is the Laplacian. Take note that the Laplacian, since the result is not a vector, the Laplacian will both be applicable to scalar and vector functions. So you just replace f here by a vector if your function is a vector. And of course, this is the divergence of a vector. The result is again a scalar. quantity, it's not a vector. And the curl. So divergence is divergence, the spreading or diverging or spread. Curl is essentially literally the curl. You curl around something. That's the curl. So this is the curl of a vector. So in cylindrical coordinates, the corresponding gradient, Laplacian, divergence, and curl are given as this, and in spherical coordinates, it's given as this. So you need to pause or rewind your video if you want to recall the different formulas on vector calculus. So let's now apply Gauss's law and determine when to use the differential form and the integral form. So in this example, suppose there's an electric field in a certain region of space, and it's given by this, the electric field is given by this vector. K is just a constant, R is the three-dimensional radius vector or the spherical coordinate na vector. So this is in spherical coordinates. So you are asked to find the charge density, rho, and if the source of this field is a sphere of charge of radius r centered at the origin, find the total charge q, and you must do it in two different ways. Okay, first letter A, the charge density, so rho. So as I mentioned earlier, if you see a divergence in the electric field line, then there must be a rho, a charge density distribution. So for letter A, we need to use the differential form of Gauss law. So from the differential form of Gauss law, just cross multiply epsilon naught, and you can now solve for rho. So it's just epsilon naught times the divergence of E. So take note that E here is in spherical coordinates. Therefore, we need to take the divergence formula in spherical coordinates. Luckily, our electric field only has one component. It only has the r hat component or the r component. It has no theta hat. It has no phi hat. Therefore, the theta component is 0 and the phi component is also 0. So this whole term here in the formula for divergence is 0. And then we are only left with this term here. Okay. Sorry. So our rho will now be equal to epsilon naught, the divergence of E, which is just 1 over r squared, partial with respect to r, times r squared times ER, the r component. So you will notice the electric field only has an r component, kr cubed. So kr cubed, so meaning I'll just multiply it directly with r squared, so it becomes k r to the 5th. Okay, derivative with respect to r of k r to the 5, so I will just take out the constant, so you have k epsilon naught. So you have 1 over r squared. The derivative with respect to r of r to the 5 will just be 5 r to the 4th. So so you have r to the 4th, r squared, so you will have 5k epsilon naught r squared, or 5 epsilon naught k r squared. So that is the charge density. So if you are asked to find the charge density given the electric field, you then need to use the differential form of Gauss's law. How about for letter B? How do you find the total charge Q? So you can actually do it in two different ways. One is using the integral form of Gauss law. So that's the difference between the differential form and the integral form of Gauss law. You can use the differential form to solve for the charge density, rho. You can use the integral form to solve for the total charge Q. So from the integral form of Gauss law, so this is our scenario, no? You have a total charge Q which is distributed in a sphere of charge of radius r. This is your Gaussian surface. This is your differential area. This is your electric field line. Okay. So using Gauss law, E dot dA is equal to Q over epsilon naught. So you can just solve for Q. So this will be our basis here. Our electric field is actually given as K r cube r hat, and our differential area vector is just the differential area vector for a sphere. So if you dot these two vectors, E dot dA, then you multiply that to r hat dot r hat is just equal to 1, and you are left with, so Q just equal to epsilon naught close integral of, so if you dot these two, you will have k r cubed times r squared, so you have k r to the fifth sine theta d theta d phi. So there's no longer any direction because this is a dot product. The result is scalar. R hat dot r hat is 1. Okay. So k is a constant, so you can take it out of the integral. And this is a surface integral, closed surface integral. So this is actually a double integral because it's a surface integral. So you have integral of sine theta d theta, integral of d phi, and then r here, our r here is just equal to the radius of the sphere, which is the capital R. So you have r to the fifth outside of the integral. Okay, so phi is evaluated from 0 to pi, and d phi is evaluated from 0 to 2 pi. Okay. This integral will give us a value of 2. This integral will give us a value of 2 pi. So therefore, our total charge Q will be 4 pi k epsilon naught r to the 5. Okay. So the second way to solve for the total charge is to use the total charge integral formula. Since we already know the charge distribution using the differential form of Gauss law, rho, then we integrate over the total volume dV of a sphere given by this equation, and you will get the same result. So I will leave the derivation to you. So this is just an easy derivation. So there's two ways here. You directly use Gauss's law, integral form, or you first use the differential form of Gauss law and then use the rho to solve for the total charge Q. So that's the different ways to use the integral and differential form of Gauss's law. So let's now have another application where we have a line charge. So this is actually the same problem that we have before in the Coulomb's law for continuous charge distribution. But here we're gonna solve the same problem using Gauss's law, and you will notice that it will be much easier. So if you are asked to find the electric field at point P, a distance s from a line charge, then you have to include or enclose your line charge by a Gaussian surface, and your Gaussian surface must also include the field point, the point where you are trying to find the electric field. So you use the integral form of Gauss law. E dot dA is equal to Q over epsilon naught, where ang Q is the charge enclosed by your Gaussian surface. So the charge enclosed by your Gaussian surface is just equal to integral dq, or in this case dq is lambda dl, where the dl is the length, differential length, or the length enclosed by your charge. So in this case, if you have a positive line of charge, then the electric field will be radial along the two-dimensional radius, so S hat. The electric field at all distance S from the line charge will also be the same. So therefore, the electric field value will be, or magnitude will be constant, and its direction will be S hat. Similarly, for the area vector, since the Gauss law equation is a closed surface integral, meaning you need to include all of the possible areas. So in this case, we have two areas. The area of the body of a cylinder, dA1, which is S d phi dz. Its direction is S hat, radially outward. And the second area vector is say dA2 is in the caps of the cylinder, which is a circle, and it's directed along the z direction. But you will notice this is a dot product, E dot dA. So if you dot the electric field E dot dA2, their angle is 90 degrees. They are perpendicular with each other. This means that cosine, that product is E dot dA is E dA cosine theta, so cosine of 90 degrees is 0. So actually, the second differential area vector will not contribute to anything. So your total, your E dot dA here, the closed integral of E dot dA, this integral will actually be composed of two integrals. The integral of E dot dA1 plus the integral of E dot dA2. This is the meaning of the closed integral. You integrate over all surfaces. So this is the integral of the over surface 2, and this is over surface 1, the body of the cylinder. But this is 0 because E and dA2 are perpendicular to each other. So therefore, your E dot dA will just be E dot dA1. So E dot this one, dA1. So we substitute this and this in our Gauss law equation. So you will have S hat that's just equal to 1. So since E is a constant, you can take it out of the integral and you are left with the integral of dA1, which is just S d phi dz. So since that is just the total integral, or the total surface area of the body of the cylinder, that integral will actually just be equal to the area of the body of the cylinder, which is just 2 pi. In this case, our radius is S and our total length is L, 2 pi SL. And this will be equal to the charge enclosed in this case. Since lambda is constant or uniform, you can take it out of the integral and then you will be left with the integral of dl, where the integral of dl is just the total length, so L. So therefore the total charge is just lambda times L, which is this one. So lambda times L over epsilon naught. So therefore I can now find the electric field of a line charge, and it's just equal to lambda over 2 pi epsilon naught S. But this is just the magnitude, but we already know its direction. This is just E, the magnitude, and the direction is S hat. So to get the vector, just multiply it, or you just take into account the direction S hat. So this is now the field of a line charge, or line charge distribution, lambda over 2 pi epsilon naught S S hat. What we have actually obtained before, and when we use Coulomb's law, is it's just X here. It's just the same, but we use the value of variable X, and then X hat. Okay. But this is now the more general solution, S hat. Okay, we didn't solve this problem in the previous lesson, in the lesson on Coulomb's law. But now we're gonna solve it using Gauss law, and you will realize that it's very easy to solve for the electric field inside and outside a sphere of charge. Okay, here uniform charge distribution. So Q is uniformly distributed throughout the volume of the sphere. So if you want to solve for the electric field inside, so you must get a sample field point inside R, which is less than the radius of the sphere, and we make a Gaussian surface inside. So since our charge distribution is spherical, then our Gaussian surface must also be spherical. So it also must include our field point. So therefore, our Gaussian surface is a sphere with radius small r. So we then use the Gaussian Gauss law integral form. So you will notice that the electric field here, see, we are assuming it's a positive charge distribution, is radially outward. It's actually along the r hat, the three-dimensional radius vector. And at all points, a distance r, so at all points on the surface of our Gaussian surface, the electric field is the same. They just differ in a particular direction. So at this point, the direction of the electric field is in that direction. At this point, the same magnitude but different direction, and so on. But that direction is r hat. The area vector is also along the r hat direction. There's only one area vector in spherical coordinates. One area of concern, rather. So our total charge enclosed here, since this charge Q is distributed along the in the whole volume of the sphere, but since our Gaussian surface is just this one within the sphere, we must just calculate the charge enclosed by our Gaussian surface. So this is the charge enclosed in this sphere is just a fraction of this total charge Q. Now, how do we find the fraction of the total charge Q? So there is a uniform charge distribution here, meaning your rho, your charge density, is also uniform. And if it's uniform or constant, it's just equal to the total charge over the total volume of the sphere. In this case, the total charge is Q, capital Q. The total volume is 4/3 pi r cubed. So you can take it out of the integral, and what will happen now? So your Q will now be rho, which is just Q over 4/3 pi r cubed integral of dV. This integral of dV is just the total volume of this, the total volume of your Gaussian surface. In this case, the total volume of a sphere of radius small r is just, this integral is just 4/3 pi small r cubed. So cancel ang 4/3 pi, cancel ang 4/3 pi. So therefore, ang total charge Q, or the charge enclosed Q, is just equal to the total charge times r cubed, small r cubed, capital R cubed. So it's actually just a fraction of the total charge Q. So similarly, so you use E, the vector form of E and dA here. So E is constant, you can take it out of the integral, so you will just have the integral of dA, or the integral of dA is just the total area of your surface area of your Gaussian surface, which is 4 pi r squared. So E times 4 pi r squared is equal to the charge enclosed, which is Q, this one, over epsilon naught. So you simplify, and you get that the magnitude of the electric field inside is given by this. And since you already know the direction, r hat, then the electric field inside a sphere of charge is given by this. So you just multiply by r hat to get the electric field vector inside. Okay. Limiting case. The limiting case for this is when your small r approaches the radius, the big R, what will happen? It will actually approach something like a point charge form. So it will become 1 over 4 pi epsilon naught Q over capital R squared, which is the electric field at the surface of the sphere. How about for the electric field outside? So you need a field point outside the sphere. So you make a Gaussian surface, including the field point. So you use Gauss law's integral form. And here, it's still the same. The electric field vector is still constant in magnitude. And it has the same direction with the differential area vector. It's still r hat direction. And in this case here, the charge enclosed by your Gaussian surface, since your Gaussian surface now envelops all of the sphere of charge, then the charge enclosed by your surface will now be the total charge Q. No need to integrate. So you will still get the same result. E times the dA, the total dA is just 4 pi r squared, Q over epsilon naught, and you will get 1 over 4 pi epsilon naught Q over r squared, and this is now the field outside a sphere of charge. So it kinds of look like a point charge, but Q here is distributed in a sphere of radius capital R. So you in the limiting case here is when R is equal to the radius. So you will notice that the electric field inside at R is equal to R will be equal to the electric field outside at R is equal to R. So this is their boundary. At the boundary, at R is equal to capital R, the electric field inside and the electric field outside becomes the same. So this means that the electric field is continuous. Hindi siya putol at the surface in this case. So for our last lesson, since we already have taken the divergence of E, our electrostatic field, let's now try to calculate the curl of the electrostatic field. So we still have the same scenario. You have an electrostatic field, a field that is not moving or changing with time. If we take the curl, so similarly with what we did, we only take the curl of 1 over r squared r hat, and that's actually 0. The curl of 1 over r squared r hat is actually 0. So the curl is actually 0 for electrostatic field. So the only way that the electric field will curl if you have an electrodynamic situation. So if the electric field is now electrodynamic, then you will have a curl. So actually, if you have a magnetic field which is time varying, time dependent, or what we call magnetodynamic, a magnetodynamic field going in this direction, flowing through a conductor, then there will be an electric field curling around it. So this time, the curl of the electric field is no longer 0 because it's now curling. It has a curl, literally a curl. So in the case of a diverging electric field, if you have a diverging electric field, it has a divergence, but it actually doesn't curl. So the divergence is not 0, but the curl is 0 because it's not curling around something, it's just diverging. So in this case, in this example, the electric field is curling around the magnetic field, and both the situation is actually what do you call this, reciprocal or symmetric. If you have an electrodynamic field, then there will be a magnetic field curling around it. So that's the relationship with electric and magnetic fields. They are actually normal or perpendicular to each other. So what's the purpose of the curl of E? So one purpose is to tell if your field is electrostatic or not. So in this example, you're asked to find which of the following electric fields is not electrostatic. So for letter A, you have this field. For letter B, you have this field. So the only way to check is to check the curl. If the curl is equal to 0, then it is electrostatic. If the curl is not equal to 0, then it is not an electrostatic na field. So for letter A, so we just take the curl. So we use the formula. So you know how to find the determinant of a matrix. In this case, we will use the expansion of the first row. So positive x hat, negative y hat, positive z hat. And then tabon method. So to find the positive x hat component, you tabon that one, tabon this one, and then you get the cross term. So partial of EZ with respect to y, this one, minus partial of EY with respect to z. So this term. So that's the x hat component. Then you have negative y hat component and positive z hat. So you do the same. Okay, let's check this one by one. So what's partial of EZ with respect to y? So this is our electric field. It has an x component, EX, EY, EZ. K is just a constant. So this is the z component multiplied by k. So does this have a derivative with respect to y? No, that's actually 0. But how about partial of EY with respect to z? EY is this term. So you will notice that EY has a y in it, so therefore this term is not 0. How about partial of EZ with respect to x? So EZ with respect to x, so it's not 0. So this has a derivative. Partial of EX with respect to z. So EX is this one. So there's no z here, so therefore partial of EX with respect to z is 0. And then partial of EY with respect to x. This is EY with respect to x. There's no x here, so that is 0. But partial of EX with respect to y. So the x component has a y term here, so this is non-zero. So we actually don't need to evaluate all of the differentials here. All what we need to do is to verify if it's equal to 0 or not. So obviously this is not equal to 0. Why? Because the x component here is non-zero, the y component here is non-zero, and the z component here is non-zero. So therefore this field is not an electrostatic field. So if it's not an electrostatic field, then it's an electrodynamic field. It changes with time. So how about for letter B? So for letter B, using the same formula, you will notice that partial of EZ with respect to y, the z component is this one. If you take the derivative with respect to y, then 2z times k, or 2kz. And that's the same for partial of EY with respect to z. And you will get 0, 2kz minus 2kz. For the y component, that is 0, that is 0. And for the z component, it's 2ky, that's also 2ky. So 2ky minus 2ky is 0. So therefore, this is 0. And letter B, the electric field in letter B is an electrostatic field. Okay. So that's the end of the lesson. So for the next lesson, it will all be about the electric potential. So one of the key components in electrostatics is finding the electric potential, because if you find the electric potential, you can essentially find anything. So actually in chapter 2 of this course, we will be tackling all about the different techniques in finding the electric potential. So that will be our next lesson for this course. So that's it for this lesson. Thank you for listening, and I will see you next meeting.